Hi. So thanks all for attending. We're very excited to be here and to talk about Slang and how we're building Solidity compiler APIs from a declarative language specification. But first, let me introduce ourselves. We are the Nomic Foundation. We are a nonprofit dedicated to building open source projects to benefit all of Ethereum developers. You might be already familiar with one of our projects, Hard Hat, the popular framework for building, deploying, testing contracts. But we also work on Slang, which is modular compiler APIs for Solidity, and EDR, which is development runtime for Ethereum. Today I'll talk to you a little bit about the evolution of Solidity and the impact that evolution has had on the ecosystem. I'll talk about introducing a language specification and how we are using it to build Slang, and I'll end with a quick demo on how to actually use it. So Solidity has evolved rapidly since inception in 2015. I think the oldest deployed and verified contract on Etherscan was since August 2015, and people can still interact with it today. That means that tools that analyze Solidity contracts need to understand not only the latest language version, but all the versions before it. They need to understand the source code. They need to be able to map it to the output bytecode. And as many of you know, or if you have tried building tools that understand Solidity, these tools need to understand all the language versions that were released. That problem is not unique to Solidity. Some languages, like for example Smalltalk, need to understand and run multiple versions of the language together. But this problem is unique to Solidity specifically because of the immutability of the blockchain. We started looking at this problem last year by reviewing the language release change logs and Solidity public documentation, and sometimes the source code of Solidity itself. We analyzed over 70 released versions, going back all the way to version 04.11. And we observed a wide range of language updates from syntax, semantics, type system, built-in functions and variables, code generation, compiler interface. I'll try to walk you through a few examples to just to demonstrate how much work has been done and put into the language over the years. So the first example is about syntax. Which of these are valid in a top-level position in source files? The first three contracts, libraries, interfaces were introduced. They have always been valid, at least since version 04.11. For structs and enums, they're started to become supported in 0.6. Previously, they were only supported in side contracts. And then global function, or source file 11 functions were supported in 0.7.1. And then constants in 0.7.4, errors in 0.8.4, user-defined value types in 0.8.8, using statements in 8.13, and events in 8.22. The second example I have is about built-in functions. So what's the result of calling a function on another contract? Before 0.5, that call resulted in a Boolean to indicate the success of the call. But after 0.5, it now returns a tuple of both the success and the resulting bytes. If you are building any kind of tool that understands Solidity code or analyzes it, you need to be aware of these changes. And you need to account for it in order to provide accurate results to your users. The third and last result I have is about expression semantics. So given the following function, it takes a uint8 exponent, returns a uint256, and it just calculates 2 raised to the power of that exponent. What's the result of calling 2 power 16? Before 0.7, this call would return 0 because the calculation was performed using the type of the operand of exponent uint8, which would overflow. The compiler would also realize this and give you a warning. But after 0.7, it would calculate the expected value, since the calculation is now performed using the type of the base literal, uint256, which won't overflow, and the compiler will not give you a warning. This incredible evolution has made Solidity one of the most, if not the most successful language for writing smart contracts, but it has also had an impact on developer tools that are written for the language. So, for example, the tools that are written for Solidity need not only to support all the previously released versions, but with every new feature that gets released, they need to perform some non-linear work to support it. They also, some of the effort to support needs to be duplicated across different projects. So for example, there are at least 3 different grammars and parsers for Solidity that are used in production today. There is SolC, which can parse only a single version of the language at a time with its own AST. There is the Antler grammar, which is used by tools like Prettier Formatter and Solhint and some other linters. There is also third-party compilers like Slang, which implement their own grammar and parser for the versions that they care about. This impact is also transferred to the user experience because users need to spend the time and effort to verify whether their tools are supporting the new language features or not. And that sometimes can lead to slowing down adopting new language features or releases until they are confident that the tools they are using can support it properly. So what can we do about this? After our initial research was concluded, we realized the need for a formal, versioned, and comprehensive language spec. But what does that mean exactly? Well, formal means that it needs to be expressed in a language whose semantics and syntax is formally defined. And that doesn't mean it needs to be defined in pure mathematical notation. On the contrary, it needs to be expressed in plain, easy to understand language. But it also needs to be defined in a language that tools can easily read and consume. For example, if we are describing grammar, we need to use something like EBNF, which a lot of syntax tools and parser generators can read and consume. If we are describing something like built-in functions and variables, we need to use a data format like JSON to encode this information so that if you're writing any tool that analyzes the Solidity code, you can easily use this data format to look up built-in functions, their documentations, and any kind of metadata you need. The official Solidity language docs are a great starting point for building this, but they're missing a few things. For example, it's meant to explain things from user perspective, but they can sometimes miss things, miss technical information about how these changes should be understood from the tooling perspective. And it does not also cover all versions. For example, it's missing version changes or version breaks that occur in patch level releases. It does not also cover built-in functions or variables or the type system. Last year, we reached out to the Solidity team on GitHub and we shared some of this information and they were very receptive to our efforts. We started a few meetings with them and they provided valuable feedback and support as we started work on this specification. And today, I'm excited to share some of this progress with you. So since we started this work, we have finished and we have completed the most comprehensive Solidity grammar that we know of today, covering over 70 language versions, starting from 0411 till today, the latest released version, I think it's 0822. It has accurate versioning information so that every version of the language describes the language elements that only exist in that version and nothing else. We're currently looking at defining binding rules for the language, including things like scopes and type resolution. We're also looking at built-in functions and variables and how they changed across different versions, and how to encode this information in a way that any developer tool can easily consume it. And in order to keep it up to date, we're currently tracking the Solidity language public announcements and releases. We're periodically updating it. We're also hoping to continue the conversation with the Solidity language team and other third-party tool developers. And we greatly appreciate their insight and feedback as we're making more progress on this. We believe that having this specification leads to a consistent ecosystem where new language features are released along with the support from the tools that the users use. And it leads to a fantastic user experience where users have confidence in the tools they are using are doing the right thing. Now I'll share some examples from that spec from the latest version we published, focusing on the syntax. Here's the example from grammar. As you can see, on the left-hand side, you can see a list of all the language versions that had changes in syntax. On the right-hand side, you'll see that the language is divided into sections and topics, each describing a certain area of the language. The syntax we chose to describe grammar is EBNF. And we are also including human-readable documentation that we compiled mostly from the public Solidity documentation. However, it's worth noting that this is missing still a lot of information. Some of these sections are missing human-readable description about language elements, and we are continuing to build it. However, we welcome any contributions to it. Please check the links I'll present at the end of this presentation on how to contribute if you like. Now, we didn't stop at just that specification. Through our own experience building tools like Hardhat and talking to people who are working on other developer tools, we realized the need for a compiler API that abstracts all of these complexities away from people who are developing language tools. And we realized the need for introducing a compiler API that all language tooling authors can use to develop Solidity tools. We are building on top of this specification to produce modular APIs, which means that you can pick and choose the parts of the tool of the compiler that you care about. For example, if you are building tools that understand syntax like formatter or a linter, you can just import a parser and use it to parse source code. If you are building things that need type information, you can create a project model in memory and use it to query information about types and variables and any other metadata that you need. The APIs we're building are covering all Solidity versions that I mentioned before, starting from 04.11, so over 70 versions. It's extensible, which means that the API we are not building the compiler as a black box, but all of these APIs are extensible. You can use the parser to parse and generate syntax trees. You can change these syntax trees, pass it back to the compiler to perform more passes. It's also self-contained, which means that it doesn't make any assumptions about the environment it runs in. It asks the user to explicitly provide all the information it needs, like source code and the imports, which means that it can run in any kind of environment, from CLI to editors. And we're even exploring other environments like running in the browser via WebAssembly, based on potential user feedback in the future. Slang is built in Rust, and this makes us benefit from the incredible memory and type safety and performance of the language. But we are also distributed in multiple languages. For example, we ship an Node.js NPM package, which means that you can easily use our, our APIs if you're writing JavaScript or TypeScript. We're also looking in the future at Python because we realize some of the Solidity developer tools are written in Python, and we're prioritizing it based on user feedback. A few months ago, we released our alpha version, which included a parser API for all language versions that I mentioned. The parser supports error recovery so that it can recover from incomplete or invalid input. It also provides an accurate byte-for-byte complete syntax tree, which means that it includes things like white spaces and comments and allows you to extract them after parsing. The byte-for-byte syntax tree also allows reconstructing the source code from the tree, which means that if you modify the tree, if you add more information, you can easily serialize it back to source code without losing any information. We are currently working on our beta release, which provides a strongly typed AST, which means that you get structs and enums and strongly typed interfaces in both Rust and TypeScript. You get APIs for visiting, modifying, and converting these source trees. And we're also working on adding type resolution and binding information, so you can do things like calculating references to variables and definitions of these variables. We're also working on integrating Slang into our VS Code extension so that we can provide things like powerful code completion and refactoring abilities. And last but not least, we're working with authors of other language tools to integrate Slang and build our roadmap based on their feedback. If you are developing any kind of framework to analyze Solidity source code, please reach out to us. We would love to hear from you about your use case. Here's a quick demo about how to use Slang and use the current parser. The first thing you'll notice here is that we're importing a language, the language API, and we're creating a language providing the version in the constructor. So here we chose to parse this simple contract using version 0.8. And that means that when we actually parse it, we will parse the input according to version 0.8 explicitly, and we will generate the correct errors if the input contains any language elements that are not supported in that specific version. The second thing you'll notice here is that when we call language.parse, we are also explicitly specifying a production kind. That means that you can use Slang not only to parse a complete source file, but you can use it to parse specific snippets. So you can use the parser to parse a specific contract, a function, or even a single statement. That's useful for tools that not only parse entire contracts or source files, but generate snippets, and it's useful for them to validate it's correct. After parsing, the next thing we do here is we check that the output is valid and there are no errors. And now there are two different ways to deal with the tree that's produced here. The first one is we can obviously operate on the row nodes that in the tree. So here we get one node, one root node, the contract definition, with 6 children, contract keyword, white space, the contract name, more white space, and open and close braces. However, that's not the most efficient way to traverse the tree. The second way which we support is using a cursor. And the cursor is an object that you can create from any node in the tree. And it has very useful APIs to go to specific nodes by index, to go to parents, siblings, children, to navigate the tree, to go to the next or previous nodes, and also to search for specific nodes using their kind recursively through the whole subtree. This is some useful links to our user guide on how to use it. You'll notice that I made the example in TypeScript, but the user guide also contains examples in Rust. This is a link to our language specification, our GitHub project, our npm crate and Rust crate, our Rust crate and npm package. The Slang team is currently 3 people, and we're hiring. Please come chat with us after the talk. We would love to hear from you. And lastly, if you have any more questions after the talk, please join us on our Telegram channel. We are very active there. We would love to hear from you. And the second QR code is for the website I just mentioned. Thank you.